So we're talking about limits at infinity, and what we mean by this is we're talking about a limit as x is approaching infinity. Okay? As x approaches infinity. Or x approaches negative infinity. Okay? Now, one of the things to understand here is that in a lot of cases, you're going to have functions approaching infinity or negative infinity. Okay? Because if you think about your polynomial functions, remember our leading coefficient test. Okay? If the leading coefficient is positive, then the function is going to increase to the right. You guys are ringing a bell? Okay? If the leading coefficient of a polynomial is negative, it's going to decrease to the right. Alright, and then the degree of the polynomial determines whether the left side is the same or different. Okay? If the degree is even, everything is the same. Okay? If you want everything to be even with people, you do the same thing with all of them. Alright, so the left side will be the same as the right. If the degree is odd, things are a little odd when they're a little different, right? So the left side will be different, it'll be the opposite of the right side. Okay? So if it's going up on the right, it'll go down on the left, or if it's going down on the right, it'll go up on the left, if the degree is odd. Okay, and that will always be true. Now, regardless of these, if you have a polynomial and you have x approaching infinity or approaching negative infinity, what can you say about the limit?
It does not exist.
It doesn't exist. We're approaching either positive or negative infinity, so we could say it doesn't exist. Okay?
So it's optional if it approaches infinity or does not exist, we can choose?
You could pick either one you want. Okay? And in fact, on the AP exam, I was talking to Mrs. Barbag about this. On the AP exams, on their multiple choice questions, sometimes they'll give the choice for does not exist. Sometimes they'll give the choice for positive infinity or negative infinity. They won't give both in the same problem because you could pick either one. But they recognize that either one is a valid answer.
I think last year on the quiz you gave us both options.
Yeah, I did.
Yeah, like a trick.
So,
Not
a trick.
You tricked us once. There it is.
That's not a trick. It's actually being generous. I let you put whatever you want. So.
It was a trick.
All right.
I think I got that wrong also because of that.
Now, horizontal asymptotes are another place, and this is really where the majority of the limits at infinity will be a specific value. We need to look at the horizontal asymptotes. Okay. Now, how do we find horizontal asymptotes when we have rational functions? Do you remember?
Oh, but it's like bigger on top. Bigger on
It's coming to memory.
Leading coefficient ratio. Right?
Oh, if it's equal. That's one of them, yes.
It is not just the higher exponent of the
Higher exponent is no vertical, right?
Okay.
The first part of the polynomial, the exponent is higher than the top.
So bigger, if it's a bigger exponent on top,
Then it's there is one at like
Bigger on top, none.
no.
there are no
Right.
horizontal asymptotes, which means we're going to end up approaching infinity or negative infinity, right?
Mhm.
So if you have a bigger degree in the numerator than in the denominator, you're not going to have a limit. You can say the limit doesn't exist. Okay? What if the degree is bigger on the bottom?
Is it 1 or 0?
It's 0.
I thought
It's
it was
0. And if you remember Bobo Button,
Oh yeah.
Bobo, bigger on bottom, it's 0. bigger on top, none. Bobo button. It's an easy way to remember it.
Hold on, what is it?
Bobo, B-O-B-O, so that's a 0. Bigger on bottom, it's y equals 0. B-O-T-N, button. Bigger on the top,
Oh,
none.
I never learned that.
So, I just learned that, I think later last year or something. So, I'd never heard it before. It was good.
Since like freshman year, I've been struggling with that.
Well, now you know. And knowing's half the battle.
3 years.
If you watch
3
the
years. I remember having a spoken class, trying to memorize that.
Alright, so now we have,
I had
we
to
know what
walk
happens
it.
when the degree on top is
I dropped
bigger.
the class.
We know what happens when the degree on the bottom is bigger. What happens if the degree is the same?
Did you put the two leading coefficients on top?
Put the two leading coefficients, the leading coefficient of the numerator over the leading coefficient of the denominator. Okay? So, here was what we learned about horizontal asymptotes. Those values for the horizontal asymptotes are what will give us the values of our limits. Okay? So let's look at that specifically here. Okay? We're looking at limits as x approaches positive or negative infinity. If the degree of the numerator is bigger, the limit is going to approach positive or negative infinity. Okay? So, like as we've said, we can say that since it doesn't approach a specific value, the limit does not exist. Okay? That's the bigger on top, none. Okay? Then we have the degree in the denominator being bigger. The limit's going to approach 0. So for example, on both of these, let's say we had the limit as x approached infinity of, let's say, the x cubed plus 3x squared minus 5 all over, 2x squared plus 3x plus 1. Alright? The degree is bigger in the numerator. That's going to approach either positive or negative infinity. Therefore, there is no limit. Okay? Here, we'd say the limit as x approaches infinity. Let's say we had the reciprocal here. So 2x squared plus 3x plus 1 over x cubed plus 3x squared minus 5. That limit is going to equal 0. This one does not exist. Alright? Then we have ones where the degrees are the same in the numerator and the denominator. The limit is going to equal the ratio of the leading coefficients. Okay? So in this case, we had something like the limit as x approaches infinity or negative infinity, it doesn't matter, of
3x squared
okay,
plus 5x.
there we go, and that we could have it over, let's say,
1x squared.
sure, minus 6x plus 20 or whatever. Okay, the fact of the matter is, as we approach infinity, and this is why this rule works, as this approaches infinity, okay, infinity squared is so much bigger than infinity. Think about that one for a sec. Infinity squared is so much bigger than infinity that really the rest of this is basically irrelevant. Because what's 5 or 20 when you're talking about infinity? It's nothing, It's the same idea as we approach 0 when we're dividing by something huge. It's approaching 0. What's 1 compared to 10 billion? It's virtually nothing. Okay, the limit approaches 0. So really, all we care about is this part right here, and check that out. That reduces down to 1. What do we have? 3. Okay, 3 over 1 is 3. Okay? Now, are there differences because of these values over here? Yes. But as x approaches infinity, those differences become negligible. They really don't make a difference that's worth noticing. Okay? So that's why that works, though. Okay? So let's run through a couple, and we're actually going to use some of the theorems that we looked at yesterday as we do these, okay? Some will just use these rules straight away, and some will use some of the rules or theorems we learned yesterday. This one, what would our limit as x approaches infinity equal? 0. Okay? Bigger on bottom, it's going to approach 0. Okay? We're going to approach 0. And by the way, the reason for that is x cubed, when you're taking infinity cubed compared to infinity squared, even if we just looked at, say, 10, if we have 10 squared compared to 10 cubed, all right,
It's almost 0.
it's going to approach 0. Let's say we had 100 cubed, so that's going to be now 6 zeros over 100, or wait, no, 100 squared, sorry, over 100 cubed. Okay? Well, now you look at it, we're down to 1%, 0.01. If we kept going bigger and bigger and bigger, let's say we did 1,000 squared over 1,000 cubed. Okay? Now, 6 of the are going to cancel. Now we're down to 1/1000th. And you can see, even though we're squaring and we're getting big numbers, compared to how much bigger the denominator is, it's still getting smaller and smaller. We're still approaching 0. Okay?
Isn't it, doesn't it work like a reciprocal function where it's, like, moving towards the 0 but never actually, like, approaches it?
Yes. It'll approach 0, and remember, that's kind of the whole
That's the
point of the
definition of-
limit.
yeah.
Yeah, that's a good observation. It never will actually equal 0. Okay? But this is why we're working with the limit. The limit is continually approaching 0. Okay? So
the asymptote is 0?
yeah, the asymptote's at y equals 0. The limit as x approaches infinity equals 0. Okay. How about this one?
3 over 7.
3 over 7. Okay? 3 over 7. All right? The degrees are the same, so we take the ratio of the coefficients. How about this one?
Isn't
3
it the
over
same?
2.
Okay? Are the degrees the same?
Mm-hmm.
Yes.
Yeah, the degree of the numerator and denominator are both
-2.
not -2.
1 over 2.
Square
1
root
over
of
2. Okay, 1/2. All right, so even though there's this -1 here, that's okay. X is still to the half power. So same degrees, you got 3/2 for your limit. Okay? And then here's your, if you want, trick question. Do you remember what this is?
Oh.
Oh,
It's like
That's actually the definition of something. Do you remember what that's the definition of?
it's like decay.
It's related.
It's like the half-life stuff. I don't remember what's the
It's kind of related.
Isn't that
Exponential.
a tax?
It's a number. It comes down to a number.
E? No, not.
Yeah, that's the definition of
Oh,
E.
yeah.
That doesn't follow any of our
It's
rules,
the
but that's
decay
just,
formula.
figured I'd throw that one in too, just as a reminder.
I would
Okay.
get that trick question.
That's E.
No, but then I would second guess and change the answer.
You change it to like pi or something. So. All right, but let's take this one step further, okay, and incorporate some of the rules that we looked at yesterday. what if I gave you, let's say, the limit as x approaches infinity of, say, 3x squared plus 4x over 5x squared minus 7 plus 6.
Isn't it 3 over 5 plus 6?
Okay? Why?
Because you can separate it and do the limit of 3 over 5 and then add to the limit of 6.
Okay, good. Remember, the limit of a sum is
Maybe
the sum of the
you
limits.
factor x in the top, so
I mean, you could, but that's not going to help us in this case. What we're using, though, is what we looked at yesterday. But here we have the limit of a sum of two functions. We have a rational function and we have a constant function, right? So we could take the limit as x approaches infinity of 3x squared plus 4x over 5x squared minus 7. And we could add to that the limit as x approaches infinity of 6. And here's where you can use the rules that we've learned, okay? Same degree. So like you said, we have 3/5 for that limit. The limit of a constant is the constant, so it's just 6 3/5. Okay? So, any questions about what we see there? All right, good. So, we have. Good, we've got some time here. All right, so what I want to use the remainder of our time to do is I've got some practice here. Here, they're having you examine some things with an exponential function, okay? And then also here we're looking at, find if possible. So you have this exponential function. You can also look at the transformations of the natural exponential function e to the x, and think about your limits in relationship to those as well, okay? So we're kind of taking it, this is just basic what we were just doing, and then 2 and 3 kind of expand it. So we're going to use the next 15 minutes or so here to do that.
Can we do 2 and 3 first?